Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, we're going to answer some of the emails I get. I get hundreds of emails concerning science, and I've gotten quite a few emails concerning, well, the movies recently. A series of questions about The Imitation Game. Who was this Alan Turing who changed the course of World War II? When was the last time you heard that a mathematician changed the course of human history and in the process pretty much created the field of artificial intelligence all by himself? And then for the matter, there's another movie called The Theory of Everything about my colleague Stephen Hawking. And the question is, well, what is a theory of everything anyway? How is that possible? I mean, the universe seems so mysterious, so strange. So how can you have a theory which claims to know everything? And then in the second half of Exploration, we can bring on a special guest, UCLA Professor Greg Stock. And we're going to talk about his book, Redesigning Humans. How far should we go to push genetic engineering? Of course, everyone believes that we should use genetic engineering to solve medical questions, to make us healthier, to eliminate suffering and disease. But, well, if you can do that, for that matter, why not redesign our genetic heritage? How far should we go? Can we create Homo superior, like in the movies, science fiction movies that talk about the universal soldier, for example? Or is it all a bunch of junk? We'll talk to Professor Greg Stock about that when we discuss genetic engineering and redesigning humans. But once again, I get a lot of emails, and I've been getting a lot concerning the movies. One movie that's been creating a certain amount of controversy is The Imitation Game. Very briefly, it's about the life of Alan Turing, a mathematician who actually helped to break the German code during World War II. According to the movie, his work led to the shortening of World War II by 2 years, because we could now understand exactly what Hitler was thinking and planning. And in turn, he saved the lives of perhaps an additional 40 million people. Well, you'd think that a guy like that would be hailed as a national hero. Wrong. His work was totally classified by the British government after the war. And unfortunately, he was arrested after the war and charged for being gay, which was illegal at that time. And he was forced to undergo horrible, horrible experiments on his body. He was injected with hormones that were supposed to cure the disease of being gay. He eventually began to grow breasts, according to biographies of Alan Turing. He became very depressed, and he committed suicide. He took an apple, dipped it in cyanide, and ate the cyanide-laced apple. Some people claim, though I'm not sure it's correct, that Apple Computers gets its name from this. If you look at the symbol of Apple Computers is an apple with a bite taken out, perhaps, just like the bite that Alan Turing took to end his life at the age of 41 when he helped to establish the field of artificial intelligence. Well, first of all, the first question I get is, well, exactly what did he do? Not only did he build a machine, the first of its type, that could break the German code, thereby allowing the Allies to read right into the plans of Adolf Hitler, to anticipate attacks, to divert what he was planning. Not only did Alan Turing do this, he also laid down the theory of computers. These are called Turing machines in honor of Alan Turing. Every time you turn on your iPod or iPad, you're turning on a Turing machine. And he wrote down the laws which every electronic computer uses even today. Not only that, but then he began to speculate about the future. What does it mean if we can build machines of increasing complexity? Will one day we be able to build a machine that is indistinguishable from a human? Well, this gets us into the question, what is the imitation game anyway? At the very end of the movie, there was a garbled attempt to explain it. What Turing said was as follows. Let's take two boxes. In one box, we put a human. In the other box, we put a machine, a Turing machine, and we're able to ask it any question we want. Here is the problem. Can we distinguish which box has a human in it and which box has a robot? Well, today, of course, the answer is pretty clear. Robots are not very smart. They're rather stupid, in fact. And you could very easily just shoot the breeze, gossip, talk about the Yankees or whatever. And it's very easy to tell the difference between a human and a robot. But what about the future? What Turing did was he ended endless speculation about the soul, endless speculation about robots being intelligent, to give you an operational test. No philosophy, no books, no poems, no songs, a test. A test to see whether or not, quote, machines can think. This is an age-old question, goes all the way back to Leonardo da Vinci and even earlier. According to Greek mythology, Vulcan, the god of the underworld that created all these machines for the underworld, well, Vulcan had created robots, according to Greek mythology, walking machines. In fact, Pandora, if you read one version of Greek mythology, is actually a robot. And Leonardo da Vinci actually designed a mechanical knight that could execute some primitive motions, and he wondered, how far can you push this technology? Well, people speculated using philosophical, biblical references to souls and spirits and stuff like that. But Turing comes along and says, bah, humbug. What we need is a test, an operational test that anyone can do, and this test has actually been done. And it's rather easy to show that you're talking to a machine and not a human being. Just ordinary gossip is enough to tell the difference. Well, then here is the question. Here is the question of questions. Well, what's to prevent it? In the future, why can't we build robots as smart as us? What's the problem? We have computers that are very powerful, machines that could be, in principle, many city blocks across if we want to. Why not a thinking machine? Well, there are at least two basic problems with building a thinking machine. The first is pattern recognition, and the second is the common sense problem. Let me explain. First of all, forget all the Hollywood movies that you've seen, like Terminator or The Matrix. Forget all those movies. We're not going to have robots anytime soon. So what's the problem? First is pattern recognition. For example, eyesight. When you walk into a room, you see chairs, you see dinner plates, you see boxes, you see things, you know what they're for. However, when a robot walks into a room, it sees circles, squares, rectangles, in other words, geometrical lines and circles and squiggles and objects. The computer does not understand chairness. It doesn't understand boxness. It doesn't understand that these objects, consisting of lines and circles, mean something. And so when a robot walks into a room, it takes hours for it to analyze all the circles and squares and squiggles and ellipses and say to itself, it's a table. That's one huge problem. Robots can hear better than us. They don't understand what they're hearing. They can see better than us. They don't understand what they are seeing. We can recognize people's faces. Computers have a hard time recognizing people's faces. We can recognize handwriting. Computers have a hard time recognizing handwriting. So pattern recognition is a big problem. What's the second problem? The second problem is even bigger, and that is common sense. We know that water is wet. We know that when you die, you don't come back the next day. We know that mothers are older than their daughters, and so that's the problem. The problem is, how do you build in the millions of lines of common sense that are necessary to understand simple common sense concepts? Like, for example, animals do not like pain, or mothers are older than their daughters. You may say to yourself, well, that's easy, that's common sense. Well, teach that to a robot. Teach a robot that animals do not like pain, or that mothers are older than their daughters, or that water is wet. And you begin to realize it's a hard problem. In fact, a 5-year-old child has more knowledge of common sense than our most advanced computer. Think about that. A 5-year-old kid knows more about water, about mothers, about objects around it. And why is that? Because, well, kids bump into reality. They see mothers. They touch water. They know that they've had contact with these things, and they can make conclusions as a consequence. Robots have not. Robots have not touched water. They've not seen mothers older than their daughters. They've not seen animals run away from pain. Robots only do what they're programmed to do. So how does Mother Nature solve the problem? Well, there are two basic approaches to the common sense problem. For the last 50 years, in some sense, we've been barking up the wrong tree. For the last 50 years, we approached it with a top-down approach. That is, we want a disk with all the lines of common sense, a disk with all the facts of water and mothers and children, and facts, for example, that string can pull, but strings cannot push. We all know that. We all know that strings can pull, but strings cannot push. But robots don't, because they haven't pushed on a string before. Well, these lines of common sense would occupy many disks, hundreds of millions of lines of common sense, and you simply put it into a robot, and the robot says, I exist. I am aware. I think I am alive. That was the top-down approach. It failed. Miserably, it failed. Because there are just too many lines of common sense. Too many lines of common sense. So now we've tried another approach, the bottom-up approach. Now, the bottom-up approach is the approach taken by Mother Nature. And that is, think of the way that a child learns. A child does not understand common sense at all. But the child bumps into things. It touches water. It knows that it's wet. It touches string. It knows that strings can pull, but strings cannot push. And that sticks can push, but sticks cannot pull. So by tedious trial and error, taking place over a period of years, decades, the kid begins to understand the rules of the game. And that's how Mother Nature does it. In other words, the brain is a neural network. The brain is actually not a Turing machine at all. In fact, Turing himself might have been a little bit surprised by that. But looking at the structure of the human brain, we know that it's not a Turing machine. The brain has no CPU, no Pentium chip. The brain has no software. The brain has no programming. It has no subroutines. It has no Windows. And so the brain doesn't have anything that we associate with a modern computer or a Turing machine. And so then the question is, what is the human brain? The brain is a learning machine. It's a neural network. It literally rewires itself after learning every task. And so you see, the architecture of the brain is different from the architecture of a Turing machine. Think of your laptop, or think of an iPod. It has a central processor, a Pentium chip, for example, which does most of the calculation. And it has a memory. And so basically you have memory and you have a central processor. That is what we call a computer. However, the brain does not have that. There is no CPU. In fact, you can actually cut out half the brain. There's some cases where you have to do an operation to remove half the brain, and the person simply readjusts and learns to operate with half a brain. So believe it or not, humans can actually survive with only half a brain. But a computer, you remove one transistor from a Turing machine, and it goes on the blink. So now you begin to see the problem. And so then the question is, well, how does Mother Nature do it in real life? Well, think of a bug. A bug is not a Turing machine. It's not programmed into its memory how to walk. The bug has to bump around. It has to fall down. It has to learn how to walk. Think of the way in which, for example, a young horse learns how to walk. It's not programmed into its brain. By trial and error, by moving its legs after it's born, a horse begins to understand how to walk. And so that's the difference between the top-down approach, where you try to program from the very beginning the laws of walking, versus the bottom-up approach, which is how Mother Nature does it, which is basically learning how to walk from scratch. And so in the last few decades, we finally began to realize that maybe, just maybe, we wasted the last 50 years thinking that we're going to get machines that think by building machines using the top-down approach. Perhaps more fruitful would be combining both. For example, on Mars. On Mars, we have the Mars rover, which walks like a bug. It doesn't walk like a mechanical man. Most science fiction writers thought that when we put the first robots on Mars, they would walk like a human. No, they walk like a bug. So it's the victory of the bottom-up approach rather than the top-down approach. And then the next question is, well, what happens when they get smarter than us? Right now, robots are about as smart as a cockroach. A lobotomized, retarded cockroach, because it can just barely walk across a room, recognizing the objects in the room. That's how primitive our robots are today. However, I can see a time in the coming decades when perhaps robots are as smart as a mouse, then as smart as a rat, then as smart as a dog or cat, and finally as smart as a monkey, perhaps late in this century. At that point, they could be dangerous. They may have a sense of consciousness, a sense of self-awareness. Their agenda may not be the same as our agenda. At that point, and we have plenty of time to prepare for this, I think we should put a chip in their brain to shut them off if they have murderous thoughts. Otherwise, we too may wind up on the evolutionary scrap heap, replaced by our evolutionary successors, our machines. Another possibility, other than simply shutting them off if they get too smart, is to merge with them. That is, to use genetic and mechanical enhancements on our own body so that we, in some sense, merge with our creations. We become, in some sense, Superman. Now, look at what we can do today. In my book, The Future of the Mind, I talk about all the research connecting the human mind to a computer. Believe it or not, people who are totally paralyzed today, totally paralyzed, can now walk. They can now move objects with mechanical arms and mechanical legs. They can operate wheelchairs. They can do crossword puzzles. They can read email, answer email. They can operate household appliances. In fact, even if you are totally paralyzed and can't even scratch your nose or roll over, it's possible to connect your brain today with a computer so that you can do anything that an ordinary human can do. Play video games, operate mechanical objects, walk. In fact, if you take a look at the opening of the soccer games in Brazil last summer, you realize that the guy who kicked the soccer ball was a paraplegic. He was paralyzed. But at Duke University, they connected his brain to a computer, which in turn controlled mechanical arms and legs, and he became Iron Man. Well, moving right along, I get another set of emails about another movie, and that is The Theory of Everything, about the life of my colleague, Stephen Hawking. And the question is, well, what is the theory of everything anyway? Isn't that rather presumptuous? The universe is so complicated. The universe is so mysterious. How can you possibly have a theory of everything? Well, first of all, there are 4 fundamental forces that rule the universe. As far as we can tell, there are 4 forces which determine the nature of stars, the nature of planets, the nature of your body. And the first force is the force of gravity. That's what holds the Earth together. That's what holds the solar system together. That's what holds the stars together. And Isaac Newton was the first one to give us a basic understanding of the fundamentals of gravity. And then it was Albert Einstein who came out with a complete relativistic theory of gravity based on the curvature of space and time. So we have a fairly good understanding of gravity. Then we have the electromagnetic force, the force that lights up our cities, the force which governs fire, which governs light bulbs and lasers, radar, microwaves, television sets, all of them based on the electromagnetic force. And again, we have a good understanding of the electromagnetic force. It was James Clerk Maxwell, around the time of the American Civil War in the 1860s, who wrote down what are called Maxwell's equations. Maxwell's equations, in turn, allow us to understand the nature of light. It's a very complex series of equations. In modern form, the equation says that the 4-dimensional divergence of an antisymmetric second-rank tensor equals 0, and that's the equation for light. In fact, at Berkeley, where I got my PhD, you can actually buy T-shirts which say, in the beginning, God said, the 4-dimensional divergence of an antisymmetric tensor equals 0, and there was light. And it was good. Well, then we have the nuclear forces, 2 nuclear forces that rule the sun. We have the strong and the weak nuclear forces. So have we been able to make headway in terms of understanding why there are four forces and why they are so different? And the answer is yes. It turns out that the electromagnetic force and the strong force and the weak force can be combined together. The weak and the electromagnetic force give us the electroweak interaction theory, and we now have the Standard Model. The Standard Model allows us to unify those three forces, that is, the electromagnetic, the weak, and the strong nuclear force. But what about a force that governs all the forces, that is, a super force? That has eluded physicists for almost a century. People have tried to create a theory which can explain all four forces and have failed. What's the problem? Well, gravity is a force unto itself. It is described by relativity, by Einstein's theory, but the quantum theory is totally different. Gravity is based on smooth surfaces. Einstein envisioned smooth curved surfaces, and we're like actors and actresses dancing on this curved surface. However, the quantum theory is choppy. It chops up matter into tiny packets called quanta, and it deals with the tiny subatomic world. While gravity deals with black holes and quasars and expanding universes, the theory of the very big, the other forces, the quantum forces, describe the world of the very small. So we see that there are huge differences between gravity on one side and the quantum theory on the other side. Well, you may say to yourself, why don't we simply put them together and just see what happens? Well, when you put gravity with the quantum forces together into a quantum gravity theory, you get nonsense. You get a bunch of gibberish. You get things that blow up, that are infinite. Makes no sense whatsoever. And so, for the last 50 or so years, physicists have tried, with varying degrees of success, to create a theory of everything, a theory of all fundamental forces, without much luck. However, there is one theory, a theory which has actually worked, a theory which does allow you to unify gravity with the other forces, a theory which is very hard to test, however, and that's string theory. That's what I do for a living. That's my day job. So a theory of everything will be a theory that explains both gravity and the other quantum forces. That would be a theory of everything. Now, unfortunately, the string theory is so mathematically complicated that people have not been able to get a firm test of the theory. And so some people can still quibble. They can still say there's a weak spot, and that is there's no direct proof of string theory yet, which is correct. We have the Large Hadron Collider, the biggest machine of science, which is built outside Geneva, Switzerland, but even the Large Hadron Collider is not powerful enough to give a full test of the theory of everything. So in some sense, the quest to build a theory of everything is in some sense incomplete. We have the theory, but we don't have a way to fully test the theory at the present time. Well, if we don't yet quite have a tested theory of everything, then the obvious question is, well, what is the theory of everything, the movie, and what did Stephen Hawking actually do? Well, what Stephen did was he took the first initial steps toward creating a quantum theory of gravity. First of all, Einstein's theory predicts the existence of black holes. That is, objects that are so powerful, so large, so massive, that gravity is so strong that even light itself cannot escape from them. So anything which approaches a black hole will eventually approach a sphere called the point of no return, or the Schwarzschild radius, or the event horizon. If you fall through the sphere, then you go into the black hole and never to be seen again. Everything checks in, nothing checks out, like a cosmic roach motel. That's a black hole. However, what Stephen Hawking said was, well, that's not right because it violates the uncertainty principle. The uncertainty principle says you can never be totally sure exactly where the position or the velocity of a particle is. If we have a black hole, well, everything is classical, everything is perfect. We know exactly where it is. We know exactly everything about the black hole, but that violates the quantum theory. Therefore, he said, black holes must be gray. There must be uncertainty with regards to its position. So, for example, according to Hawking's calculation, there should be a faint glow a faint glow that emanates from the black hole. And as a consequence, black holes get less and less energy with time. They actually decay. This glow is called Hawking radiation. At the present time, it's too weak to measure. However, we have seen black holes in outer space, but the Hawking radiation is too faint to measure. And so that's why I think Stephen has not won the Nobel Prize in Physics yet, because it's not possible to get a direct test of Hawking radiation. However, Hawking radiation would solve a lot of very thorny questions. For example, if you throw the encyclopedia into a black hole, what happens to all the information contained in the encyclopedia? Well, originally, Hawking said that the information must be destroyed, and that violates the quantum theory. The quantum theory says that no, information cannot be totally destroyed. It must be somewhere in the universe. If I burn a book, for example, it appears as if all the information of the book vanished, but that's not quite true. If you could retrace all the positions of the molecules, you could reform the book before it was burned, so the information is not totally lost. Of course, it's impractical to do that, but in principle, it's possible. And so quantum theory says that you can't really lose information. Well, Hawking is a semi-classical physicist. That is, he's not fully quantum mechanical. And so he said that, well, in this situation, the quantum mechanics must be wrong. Well, now he's changed his mind. String theory has come along and given us a theory of black holes, which we think can adequately describe all the mysteries of the black hole. And when you look at the string theory black hole, you realize that information is not destroyed. And ironically enough, where did this information go? Ironically enough, it went into Hawking radiation. So when you throw the Britannica into a black hole, the black hole oozes out a very faint glow, and in that glow, if you were smart enough, you could reconstruct the Encyclopedia Britannica. Of course, in practice, none of that is possible, but in principle, it is possible, we think, that by looking at the afterglow of a black hole, you can see the tracings of the information that you dumped into the black hole to begin with. So the conclusion is, we do think that a complete theory of gravity is possible. It would be a quantum theory. However, we're not yet certain that we can prove that this theory is string theory, which is what I do for a living. So to summarize, one of Hawking's great contributions was he was one of the first to take the initial steps to combine gravity with the quantum theory, allowing us to create something called Hawking radiation. However, a complete theory of all fundamental forces that is universally accepted, universally tested, still eludes us. We have string theory. However, string theory has not been fully tested, and it may take quite a while to get a full test of the theory. So the theory of everything is not yet in our grasp. And now I'd like to introduce our special guest for today. We're very delighted to have with us Professor Gregory Stock of the University of California at Los Angeles, where he's the director of the program on medicine, technology, and society. And he's the author of a very controversial book called Redesigning Humans. That's right, Redesigning Humans, Choosing Our Genes, Changing Our Future. In other words, we're not talking about something that's going to happen anytime soon. But perhaps 50 years, perhaps 100 years into the future, who knows for sure, we may have the ability to tinker with our genetic heritage. And then the question is that a good thing? Is it a good thing if every parent can begin to choose the characteristics of their children? What about the future of the human race? What about medicine? What about ethics? These are the questions we're going to be exploring with Dr. Gregory Stock of UCLA, author of the book Redesigning Humans. Okay, the first question for you, Dr. Stock, is how did you first get interested as a youth in biology and medicine?
Well, I've sort of been interested in the issues of life for as long as I can remember, and I think the epiphany that I had being as a graduate student just about to get my doctorate in molecular biology was that suddenly I was walking on campus and realized that I didn't really know the difference between an oak tree and an elm tree. And I realized I was at too much of a molecular level, so I thought it would be worthwhile for me to step back a little bit and look at more systems biology.
Okay, and why did you specifically get interested in the whole question of genes, genetic modification, and genetic enhancement?
Well, I was developing some ideas related to sort of levels of complexity in life, and that there are multiple very distinct levels of complexity, the lowest being that of bacteria, which is just essentially a little bag of biochemicals and no internal structure or anything. And then animal cells, or eukaryotes, are 1 million times the volume. They have all sorts of compartments. They are much, much more complex. And it turns out that the origins of some of those components were, in fact, bacteria themselves, which came together symbiotically and then formed really complex organizational structures. And then this happened again with the formation of multicellular life, all of the complex multicellular organisms, the animals and plants that are filling up the environment that we see, that we can observe around us. And now there's yet another step that is occurring where, led by human activity and our fusion with telecommunication technologies and all sorts of things that are drawing us together as a very integrated sort of a superorganism, the implications of that are really profound for not just human society, which is actually an organism and can be seen very clearly as that if you look into it in detail, and that's the subject of a book I wrote called The Fusion of Humans and Machines into a Global Superorganism. And I was interested in what the biggest implication of that was, and things like space travel and such are some of the products of that collaboration. But the most interesting for us, I think, is the way these technologies will then be turned back upon ourselves and reshape our own biology. And so that's how I really got interested in the sort of genomics and the various ways in which these, extraordinarily precise and powerful technologies were beginning to have the possibility of reshaping human life itself.
Okay, and speaking about reshaping human life, some people get a little bit squeamish when they think about that. They remember what happened with the Nazis and eugenics. However, isn't it true that historically, humans have in fact been enhancing other species, like dogs? Haven't we been breeding dogs for thousands of years? And what about plants as well?
Yes, it's definite that there is not, this is not something new. It's just that the tools that are being brought to bear upon biology are so much more sophisticated. So I think that canine breeding is an excellent example, and is actually going to serve as sort of a pilot project for our own self-modification, in that here we're using the most kind of primitive tools of selection and breeding. And look at the diversity that exists in the canine realm. I mean, it's truly extraordinary. And so to think that when we're sort of exerting control over our own reproductive possibilities, essentially through in vitro fertilization, through genetic screening, all of these sorts of things, that there won't be significant implications for us as a species, as individuals, as cultures, I think is very much putting one's head in the sand just because of all these previous examples.
Well, let's look at the pros and cons. The pro side would be that dogs are very plentiful and successful in North America, while Canis lupus, the gray wolf, is near extinction in many areas. And so the dog benefited by genetic enhancement being close to humans. But dogs also have lots of genetic defects because of all the inbreeding that took place over thousands of years. What are your thoughts?
Well, I think that there are inbreeding issues, especially with certain breeds. I believe that that many dogs have a longer life expectancy, certainly, than the gray wolf in the wild. But yes, there will be consequences of that sort, and especially when you have with sort of crude, the kinds of selective tools that one uses and in natural breeding. You're much more likely to get these sorts of issues because you have large clusters of genes that are exchanged and you have inbreeding problems and such. I would imagine that those will be less significant when this occurs in humans for several reasons. One is that the advances in medical technology are such that they mute some of the problems that might otherwise be significant. For example, the most obvious, or a very obvious example of that is eyesight, where virtually everyone over the age of 40 requires glasses, and we wouldn't be very functional without them. And yet we don't even look at it as a disability. And there are a variety of other kinds of what would have been even fatal diseases that no longer are such. And in fact, that has had a huge impact in the spread of various mutations that would otherwise be very, very debilitating because we survive longer. We reach reproductive age when otherwise we might not have. So I see that as one reason that these are less likely, that they are unlikely to be things that we can't deal with. And another is that we're really understanding human biology and life in general in a much more profound and nuanced way.
And also look at our dinner table. Believe it or not, much of the foods we eat for dinner have been genetically enhanced by humans over thousands of years. But if you look at corn, even though corn was domesticated by Native Americans, corn cannot exist without humans. The kernels don't fall off without human intervention. Therefore, corn is very plentiful, very shiny, very tasteful, but it is totally dependent upon humans for reproduction. Without humans, corn cannot exist. What are your thoughts?
Well, my thoughts are several in that. First of all, virtually all of the foods that we eat are the product of human breeding in one way or another. So the idea that there are natural foods is it demonstrates an ignorance of the whole process by which all of the grains and staples that we eat are how they evolved. I mean, a potato was a little thing the size of a pea, for example, and the same thing as you mentioned with corn. The second is that I agree that we're likely not to be able to survive in an environment that it does not have technology. And in fact, that's already the case, not just because of our biology, but look at our population. We couldn't support the human population without the kinds of high technology agriculture and such that we have. And so the population is way beyond the level that we could live in a subsistence kind of a lifestyle. Many individuals who give birth to children, and they wouldn't be able to do that outside of a hospital. I mean, you have all sorts of interventions, which those interventions make it more likely that such problems will be more significant, not less, in the future. So I think that we are definitely increasingly adapted to a high-technology, human-centered sort of an environment, and the idea that we're going to go back in some way or would even have the possibility of doing that, I think is there is no real possibility that could occur.
Okay, so we talked about the past where everything, including our dinner table, dogs, cats, horses, sheep, all of them have been tinkered with and enhanced to some degree by human intervention. Now let's talk about today. We see science fiction movies where life forms can be manipulated at will, but isn't it true that gene therapy, the simplest example of just fixing a broken gene, that's really in its infancy? And that there's really only one disease that can be so-called cured using gene therapy, and that's called the bubble boy syndrome, or SCIDS. So aren't we at the beginning of this technology?
Very much at the beginning. I would differ sharply, though, with your assessment that that is the simplest of the sort of interventions that one can think of. It's actually probably the most difficult, and the reason for that is that if you're going to try and do genetic interventions, you have to find a mechanism for putting in place a significant segment of DNA. And the control mechanisms to determine when that would be turned off, on and off appropriately, and then get them into individual cells in an already existing body. That's a very, very difficult and challenging process, and an unnatural one in many ways, in the sense that the much easier and simpler way to do that would be to select or alter the genes that are in the first cell of the human embryo, and then they would be copied into every cell in the human body, along with structures that would turn them on and off, orchestrate their activity at the appropriate times and places. And that's kind of the way our genetics works naturally, in that we have every cell in the body has the same genes. It's just that different clusters of them are turned on in, say, bone than in skin or in neural tissue. And so these are the kinds of things that are possible and are much, much simpler than genetic interventions, which I think Jim Watson said that if you waited to do germline intervention, which are those that are to embryos and single cells, that if you waited for somatic engineering, the kinds of genetic interventions that are done today, to be successful, you'd wait until the sun froze over.
Okay, well, if you are Jewish, you have to worry about Tay-Sachs. If you are Caucasian, you have to worry about cystic fibrosis. And in fact, in Brooklyn, there's even a group of Orthodox Jews who get screened, and if the embryos, via implantation, if the embryos carry the bad gene, you can reject them. And in that way, they hope to literally eliminate that gene from that population. So what are some other ways in which people today can actually begin to tinker with the genetics of their children?
Well, you mentioned it right there with actually creating a number of embryos during the process of in vitro fertilization, where you take an egg and a sperm and fertilize them in a petri dish, allow them to come together in a petri dish, and then you wait until they grow up to, say, the 6 or 8 cell stage. You remove one of the cells, which isn't damaging to the embryo, and then you run a genetic test on that cell, and depending on the results, you decide whether to use or discard that embryo. That's done to avoid cystic fibrosis, to avoid Tay-Sachs. In fact, in the Jewish community, there are people have genetic tests and use that as to avoid marriages that would likely lead to children with such problems, and that's a common thing as well. So the idea of genetic screening is the easiest way that you could exploit the possibilities of these new technologies, because there you're not actually altering or changing, you're just reading out the genetic code, which is something that we can already do, although we'll be able to do it much more easily and rapidly and in more sophisticated fashions, and then making a decision based on that. So there is no risk involved, essentially, or very, very limited risks involved. And that, I think, is going to be the first application that is widespread, and that will happen relatively quickly.
Okay, now let's look at maybe a 20-year timeline, and then we'll look into the next 100, 200 years, which, of course, borders on science fiction. Mm-hmm. But let's take a look at a 20-year timeline. What kinds of therapies, what kinds of procedures are going to be available within that time frame, a 20-year time frame?
So in a 20-year time frame, I think there will be some sort of niche technologies which gain a lot of publicity today but aren't really very interesting, things like human cloning and such, which I think, even if broadly available, would only be used by very small numbers of people. The kinds of genetic engineering technologies which I've discussed at length, where you'd actually go in and alter chromosomes and add clusters of genes and such, those almost certainly will not be used other than possibly in animals, and they're already being used a little bit in animals, within that time frame. The kinds of things that will be dramatically more sophisticated and will be widely available within a 20-year time frame will be the genetic screening technology that we just discussed. And there one will be not only screening for genetic diseases, which is already done today for a few genetic diseases. It'll be done much more broadly and in a much more nuanced fashion. But I believe that there will be choices being made based on matters of temperament and personality and predispositions that involve risk for certain, for manic depression or other kinds of disorders that, are only on the borderline viewed as diseases. And so there will be basically prospective parents will be exerting choices over the genetic makeup of their children based on their individual preferences and wants.
Okay, let's talk about that now, because let's look at a 20-plus year horizon, 20, 50-year horizon, let's say, when some of the genes for attractiveness are isolated. There was a blip in the media the other day stating that shoppers spend more time taking care of their attractive children than they do with their unattractive children. And parents, of course, spend thousands of dollars on violin lessons for their children and SAT lessons to enhance their children to get into college to increase their reproductive success. But wouldn't parents therefore be hardwired not just to give violin lessons, but to actually make the children more attractive?
Well, almost certainly to pick certain traits. I think one gets into surprising choices that people would make that some of us would not consider to be enhancement, but would be so in the eyes of the parents. And what I'm referring to is, for example, that deaf parents have already, I've spoken to deaf parents who have said, interacted with deaf parents who have said that they would use such technology to ensure that their children, not that their children were hearing, but that they were deaf, so that they could fit better into the environment, that they could, into the deaf culture, that they would be able to interact more with them as parents. So the choices that people make are very interesting. Some people would like to enhance one's IQ and intelligence. Another would be interested in aspects of physicality or in appearance. And I think there will be very, very, very diverse choices that are being made. But yes, parents will definitely want to make those choices, and in fact will make those choices.
And in fact, if you just found out that the Joneses next door had their kid genetically enhanced, and your kid, who is not enhanced, has to compete against the Joneses kid, won't you therefore make a beeline to the nearest genetic enhancer so that your kid is competitive against your next-door neighbor's kid?
Yeah, maybe. It's sort of interesting, though, because the difficulty of you applying the technology will be directly proportional to the amount of enhancement that one exerts. So to actually create, for instance, super children in one way or another, no matter what the trait is, will be very complex and very slow in coming, whereas the possibility of improving some vector of performance from below average to average or average to slightly above average will be much, much easier. So there'll tend to be a leveling that will occur when these technologies are applied. I think of it as like giving parents the ability to create a virtual projection of some of the aspects that would likely be manifested in future children, and then to make choices among those virtual siblings that would be represented by embryos. So yes, it could create significant enhancements in various dimensions, and do it very, very rapidly if, in fact, for example, what we know about the genetic basis for IQ, which is not insignificant at all, certainly probably over 50% from twin studies of identical twins reared together and reared apart, a whole variety of studies in that realm. If you could identify the many genes that are involved in that and make choices based on them, you would, within a single generation, parents would probably increase the IQ of their kids by perhaps 20 points when if that was what really interested them. So that's a huge step in a very short period of time. And I think that there would be movement in many, many different directions so that there would sort of be a radiation of human form.
Okay, well, let's take these one at a time because you raise a whole bunch of things. Strength. Just recently, scientists have been studying a gene which makes a mouse muscle-bound. The mouse has tremendous muscles. They call that mouse a mighty mouse in the media. And that gene or a counterpart of that has been found in children now, human children. And the question is, what does it mean to be an Olympic sportsman or sportswoman? What does it mean to be a Yankee home run batter if it's all just a question of genetic enhancement?
Well, I think it's going to be a real interplay of many, many factors, of which genetics will be a very, very important one and a requirement, essentially. That, I mean, if you know relatively early on today whether you have the genes, whether you have the physique that you're going to be competitive at a world-class level, that you even have the hope of being competitive in various sports. And you'd have to combine with that an incredible drive and an environment that nurtured that. I would say that if you had 50 clones of Michael Jordan, that not all of them would be superstars. That there would be other factors that would intervene to avoid those, to interfere with that or to prevent that in one way or another. But, so what does it mean to be a superstar? Well, today, it used to be that there were amateur athletes, and now today, for somebody to perform at a world-class status, in a sort of a world-class status, you have to basically be devoted to a sport from a very, very early age and make it your career. And that certainly wasn't the case. So the sense of what it takes to be a professional at a world-class level will just continue to be refined. And I suspect that you may eventually reach the point where it's like having a race car, where, there's a whole team, including physicians and others, that are the support sort of group for any world-class athlete.
Okay, well, we have numerous steroid scandals, and we believe in a meritocracy, that you should work at being a great athlete, not simply take a steroid and hit the ball out of the ballpark. And yet here we're talking about something even greater than steroids, actually literally changing the genetic structure of your muscle and bones, right? So won't that also create a scandal?
Well, I think it will create a change in the way people look at these things, because as it is right now, the idea that there is going to be sort of a natural Olympics in some way, or that there are sports where people do not use various aids of one sort or another. That's really, as we've seen in baseball, that's really not the case. And the idea that we're going to be able to enforce those things is very unlikely as well, because the monetary rewards are too significant for success. And so it's just a constant battle between those who are trying to enhance in one way or another through genetic, through drugs, through all sorts of things, and those who are trying to discover those. And actually, there are certain incentives for the sports organizations to see increased performance. It'll be interesting to see what will happen to the perceptions of the game if, in fact, performance settles back and isn't as strong as when, new home run records were being set. So I think that as we move ahead, that it's going to become increasingly accepted that we manipulate our bodies in a variety of ways using interventions. What we will not want to see is ways in which these are dangerous interventions. But I would like to say, what are you going to do if, in fact, there is something that you could take that would increase performance or increase one's memory or increase any aspect of one's functioning, and, in fact, is not dangerous, where there are no side effects that are adverse? It's sort of a recreational drug of sorts, but one without the side effects of many of the ones today. Are we ourselves not going to want to take those? I mean, remember, we take things to put ourselves to sleep, to wake ourselves up, to kill pain, we intervene in all sorts of ways with legal pharmaceuticals. So the line between what is a pharmaceutical and what is an illicit drug is going to be an increasingly arbitrary one, and those discussions will seem a little bit surreal as we move forward.
Well, I'm afraid that's it for Exploration. Once again, in the first half of Exploration, we answered some questions that I get from email about the latest movies, including The Imitation Game and also The Theory of Everything. And in the second half, we brought on UCLA professor Greg Stock talking about redesigning humans. How can it be done, and how far should we go? Once again, this is Dr. Michio Kaku for Exploration.